what we are talking about the birth and death process, no? What is this? This is nothing but it's a continuous time Markov chain such that in general your state space is a 0, 1, 2, 3 and so on. It's kind of the number of population you can think of, that is the state space, and then the rate matrix Qij is 0 whenever I minus j is greater than 1. That means the transition from state I can only go to I minus 1 or I plus 1 state. Okay, so whenever it go to I to I plus 1, we say that birth occurs, and whenever the transition from I to I minus 1, then that means death occurs. And I denote this one lambda I, which is your Qi I plus 1, okay, the rate of transition from I to I plus 1, and then mu I put it Qi to I minus 1, and then actually you can write down your density matrix Q, as you know, I have wrote down. So what it represents that if I think of that lambda I of h plus small o of h for infinitesimal small h, which is basically it represents the probability of birth in the time interval, say t to t plus h for infinitesimal small h. Okay, and hence your mu I of h plus small o of h, this again gives the probability of death, the time interval t to t plus h. Okay, and now whatever we are considering, that is there any conditions so that the birth and death process has stationary distributions or not? Okay, so for that, what I have to show that to find out the stationary distribution, what we have to consider, we have to solve these equations by q, which is equal to say 0 vector, and then summation over I is in your s, pi of I is equal to 1, is it not? So q your statement which is your rate matrix, and pi, which is the vector pi I. Okay, so pi I is equal to 0. So if there exists stationary distributions, then I know that it should satisfy this equation. So it's kind of the trial and error technique that I'll try to find out the conditions under which there exist stationary distributions for this birth and death process. Okay. So for that, what we have seen that now if you look at your Q, already we know how the Q looks like. So Q is nothing but something like that. I have minus lambda 0, then 0, 0, 0, and so on. Then you have your mu 1 minus lambda 1 plus mu 1, then lambda 1, 0, 0, and so on. Okay, so now if you look at your Q and then pi, then from there what I have, from the first things I have minus lambda 0 pi 0 plus mu 1 pi 1 is equal to 0. And for the I greater equal to 1, what I have, that lambda I minus 1 pi I minus 1 minus lambda I plus mu I of pi I plus mu I plus 1 pi of I plus 1 is equal to 0. So from there you have kind of some, the rule is we are finding that mu I plus 1 pi of I plus 1, it is same as my lambda I of pi I. Means I can think of minus, this should be your mu I of pi I minus lambda I minus 1 of pi I minus 1. Okay, again if you replace it I by I minus 1 and so on, what we end up with, that is actually 0. So that means I have that pi I plus 1, you can write down lambda I by mu I plus 1 of I for I greater equal to 0. Is it not? So from there what we have considered, we have seen that because that summation over pi I over I in S is equal to 1. From there, what I have that if that pi of 0, I consider this is 1 plus summation over n is equal to 1 to infinity. Then I have product of I is equal to 0 to n minus 1. Now I have lambda I by product of I is equal to 1 to n of mu I. This in, but that means if this infinite sum is convergent, then I can find out my pi 0. So as long as you have your pi 0, then I can use the definitions from here. So now you have these summations, product things, and then pi 0. Okay. So what it says that if you have, so just looking from there, if I know lambda I mu I such a way that this summations is convergent, this series is convergent, so then I can say that, okay, for that Barth process, we have a stationary distribution. Not only that, the vector pi I, okay, the invariant measure pi I, it is given by in these formulations. Okay. So as a simple consequence of that, if your state space is say finite, if S is your finite, okay, so then what happened that if state space is finite, then I know that this summation is always finite, and stationary distribution exists. So for that, if I choose a lambda I is positive, mu I is positive, and if it is finite, so it is positive recurrent, and so on. So from there, actually, I can say that for a finite state space death and birth process, stationary distribution always exists. Okay. Okay, and then you can find out what will be your pi of i's. Okay, the stationary distribution for that case. So today I'll talk about a simple example that is called the linear growth with immigration. Linear growth with immigration means basically what I'm saying, it is again a birth and death process. It is called a linear growth process if the birth rate, say lambda n, it is given by lambda n plus a. So a is kind of the rate of immigration you can think of, and then mu of n, this is linear, so it is kind of n times of mu. Okay, it is linear with it is the n, so you can think of the state space 0, 1, 2, so on, and all these things. Okay, so it is a death and birth process where the birth and the death rate, say lambda n and mu n, are given by lambda n plus a, mu n plus a. For my lambda mu a, they are positive. Okay. Okay, so such process occurs naturally, as I said that it is on the biological reproductions and population growth. Okay, so now I have lambda n and mu n, and so then what will be your equations, or from the Kolmogov's backward equation or forward equation, what I have, you can use whatever you want. So I am using here the Kolmogorov forward equation. So from the Kolmogorov's forward equation, what is this? That means p prime t, which is pt times q. Okay. So in that case, what I have in this case, that pi0 prime of t, already we have wrote down, no? So in particular in this case, this is minus a pi0 of t plus mu pi1 of t. Okay, so in this case, this is n equal to 1, this is n is equal to 0, no? N is equal to 0, 1, 2, and so on. So I have minus a pi0 t plus mu I1 of t, and what about for p any ij prime of t for j greater equal to 1? This should be lambda times j minus 1. Just look at the general means, for birth and death process, I wrote down the Kolmogorov forward equation and Kolmogorov backward equations. Now I have choosing this particular lambda n and mu n. So if you put there, then what you have here, something like that, lambda j plus 1. plus a times p I j minus 1 t, and then plus lambda plus mu of j plus a of p I j of t, and then plus mu of j plus 1, then I have p I j plus 1 of t. This holds for all j greater or equal to 1. Okay, so that I am getting from the Coulomb-Gauss forward equation. So you can also use Coulomb-Gauss backward equations, but you have then the different expressions for that. Okay. Okay, so basically here what I try to determine the mean population size for large T. Okay, so that means if you define your MT, which is your expectation of XT. Okay, this is expectation of MT, that is the basically mean population size. And then I want to find it for large T, that means what happens as T goes to infinity. Okay, so what will be the mean populations and so on. That you will see that depending on my rate, lambda and mu, you will see it. Okay. So obviously that if lambda is greater or equal to mu, if that means the rate of birth is more, then you can expect the expected number of population as t goes to infinity, that goes to infinity, no? Because you have more number of birth compared to less number of death. So you can expect that here also you will see that as m2, as t goes to infinity, my m of t, which is the expected or the mean population size for large for the mean population size for this linear growth with immigration, that converges to infinity. And then what happened if lambda is less than mu? If there is a the birth rate is less compared to your death rate, so then since immigration is going on, then actually at t large enough, so you'll see something. Okay, that is depending on also the immigrations and so on. Okay, so let us try to find out how to calculate my m of t. Okay, so what is my m of t? This is expected value of xt. Then I can write down this is nothing but summation over, because xt where it is taking j is equal to state space is 0, 1, 2 and so on. So then I can think of this is nothing but j times pij of t over j. Is it not? J times pij over t over j. Okay, so now if these things, then what I have, because I try to find out some differential equations of my m, okay, the expectation of xt. So then what I have, what is my m of prime of t? This is nothing but summation over j of pij prime of t. Okay, j is in your s, or that is summation of j is equal to 1 to infinity. You can think of, so this is j is equal to 1 to infinity. Okay, so now what is my Pij? I try to replace Pij from Kolmogorov forward equations here, Pij prime. Okay, so then what is this? This is equal to summation over j is equal to 1 to infinity j times. Now I am considering lambda times j minus 1 plus a of Pij minus 1 of t, and then plus lambda plus mu times j plus a of Pij of t, and then I have plus mu of j plus 1 Pij plus 1 of t. Is it not? So now I am just writing down. So this part, what I can write down, this is from the first part, I have lambda times summation over j is equal to 1 to infinity j into j minus 1 pi j minus 1 over t. Okay, and then what I have, so now if you look at the Pij, that should be plus lambda plus mu times summation over j is equal to 1 to infinity. Now I have j square, okay, and then I have Pij of t. And then whatever I have from here, plus mu times summation over j is equal to 1 to infinity j into j plus 1 pi over j plus 1 over t. Okay, now I have to use also the another term, this a times this part. So this is plus a times summation over j is equal to 1 to infinity. This is j pi j minus 1 over t, and I have another form that is minus or plus. I made it. Okay, it should be minus, no? Here, this should be minus. I made mistake maybe. Okay, so this should be minus then. So this should be then minus, and then I have minus a times summation over j is equal to 1 to infinity. I have j pi j of t. Okay, so now idea is basically since j goes to 1 means the S, which is my state space, is like between 0 up to 1 infinity. So I try to find out all these things in terms of Pij. Okay, because as I told you that I want to find out a differential equations for MT, and then I try to solve it the differential equation to get my MT. So, and MT is in terms of your Pij over j and so on, summation over j. So that is why now I have different ij minus 1, ij, and then say ij plus 1. So I try to put it in a ij form. So now if you look at this part, if you just take say a, then what I can write down my a, these things actually I can write down the first one is a times, now summation over. So if I put j minus 1 is equal to some j tilde, okay, then your j tilde goes to 0 to infinity. So j is equal to what you have, or I can put it 0 to infinity. I can put j tilde, I denote again by your j. Okay, so this should be then j plus 1 Pij of t. Okay, and then minus I have a. So now j is equal to 0. This basically gives you 0. So I can put this is same as my j is equal to 0 to infinity. Okay, j times Pij of t, because as j is equal to 0, this goes to this is 0. So I'm just adding 0. Okay, so now this is nothing but a times summation over j is equal to 0 to infinity. What I have Pij of t. Is it not? So now this is summation over j. J is in from your state space, and I know from the properties of your transition probability matrix that gives you 1. So this is nothing but my A. So I have this term A is equal to my A.
So can you just repeat how that this equality for A, how you got once again?
Yeah, that's same thing. See, this one is j is equal to 1 to infinity j pi j minus 1 t.
Janus.
I told you that I try to write down everything in ij.
Okay. Okay, sir.
Okay, so now you consider j minus 1 is equal to some j tilde. Okay, so now j is running from 1 to
Yes, sir.
infinity.
That we just made the substitution for the series.
Exactly, that's the substitution, and then I denote as the same j, means j tilde is
Right, sir.
j tilde
Dummy,
the same.
dummy variable just.
Okay, and then you have, so this j pij one got cancelled out. Whatever remaining term is summation over j p ijt, and this one is nothing but 1 by properties of your transition probability matrix. So that gives you A. Okay. So similarly, I try to find out these terms, these three terms. Okay. Okay. Let's, if you just denote it that as say B, then what is my B? Okay. So now B in this case, whatever I have, this is, I can again put it because this is j minus 1 is there. So I can put this is lambda times summation over j is equal to 0 to infinity. This is j minus 1. So now j should be replaced by j plus 1. That means I have j into j plus 1. Is it not? And then Pij of t. This part I have. And the middle term, it remains as it is. So I can put lambda plus mu summation over j is equal to, now I can put j is equal to 0 to infinity, because adding, no, because j is 1 to infinity there, but since j square is there, so if you add 0, no problem, so that I can put j square of pij of t. Okay, so now third term, what I can write down, this part is plus mu times summation over, that is I have pij plus 1. So now if you substitute j plus 1 is equal to some j tilde, then whatever you have, then j tilde should be from your 2 to infinity, and now your j into j plus 1, that should be replaced by j into j minus 1. Is it not? So something like that, j plus 1 goes to your sum j, or j tilde, and then later actually I replace j tilde by j, because this is just the indices. So in that case, you are saying that it should be from 2 to infinity, j to this part, and then pij of t. So now this part again I can rewrite as, because for j is equal to 2 to infinity, if I put j is equal to 1, because of this factor, for j is equal to 0 and j is equal to 1, that gives you 1. So I am again adding 0. This factor I can write it as a mu times summation over j is equal to 0 to infinity, j into j minus 1 times pij of t. Is it not? That's the substitutions I am doing. So at the end, what I have, now you can have this summations form. Okay, so what I have here, so now this you look at j square pij lambda j square pij, so from here minus lambda j square pij, that got cancelled out. Okay, so and then you have minus mu g square pij, so from here you have your that plus mu j square pij. So the remaining term is from here one term, which is lambda summation over j is equal to 0 to infinity pij t, and from here we have minus mu times pij t. Is it not? So what I have, lambda times summation over j is equal to 0 to infinity j pij of t, and from here I have minus mu times summation over j is equal to 0 to infinity. This is same as my this one. Okay, so this is j times pij of t. Is it not? So this is nothing but my lambda minus mu times summation over j is equal to 0 to infinity j of pij of t. This is same as your j is equal to 1, and hence this is nothing but my lambda minus mu of my m of t. Okay, so you end up with, so the expected or the mean population size for this continuous time Markov chain xt, it satisfies the following differential equation. So mt satisfies the differential equation. What I have, that m prime t, which is equal to a, already I have this capital A is equal to small a, plus, and then b I have calculated, this is nothing but lambda minus mu times m of t. So it's a linear differential equation, no? So actually using the method of variation of parameter, you can find out the solution. Okay, so now suppose the initial populations, or the initially size of your populations is say I. Okay, so then what happened, that m of 0 then should be I. Okay, so with initial condition m of 0 is equal to I if my x of 0 is equal to I. Is it not? So that means, what is xt? Xt is nothing but the size of the population at time t. Okay, so what it says, that if initially there is a ith number of population, then what is your m0? This is expected. That's basically I. That is your initial population. Because I need to solve this differential equation, so I need then the initial condition is a first order ODE. So I have the I need initial conditions. So for this case, what is the solutions to this problem? You check it yourself. So thus the solution of this equation is empty. You check it. This is 80.